This conference will now be recorded.
Okay. So I think in the last session, it was pretty short. We had a 1.5 hour session, right? We were basically discussing the response model, right, that we were trying to create using logistic regression, right? So we started off with the use case. We understand that the use case is basically, to kind of understand the possible respondees who may respond for a particular campaign, right? So what happens is like, when you want to run a particular campaign, it's going to cost a lot of money, lots of dollars. But, you may not be able to, have the freedom to go back and run campaigns on literally everybody. You just have to choose the best of those people. Now, ideally, the person whom you want to probably kind of activate, or probably the kind of person from where, you can kind of derive more monetary value. So based on certain characteristics, you just have to go back and choose the customers who are more suitable, more probable for this particular campaign. That is exactly what we're going to do. We create a customer response model. We're leaving it to statistics and machine learning to do the decision making here. So our predictive models are going to go back and they are going to choose the right people saying, hey, I think these are the guys who are more likely to respond for your campaigns, rather than just leaving it to some other kind of basic analytics that you could do, or probably some kind of basic intuition that some person is going to come up with, right? So we are going to be creating predictive model here, where this predictive model is going to go back and choose the right customers on whom the campaign will have to be run, so that they're going to be, the people with a high probability who can respond to the campaigns. So that is exactly what is the response model actually going to try and help with us. Okay. So what we did was we did discuss about the data set, I think, in the previous class, right? And we even started off with some basic data quality checks, right? So we went ahead and imported the data. We looked at the data types and all. I think the date type was something of a problem for us. We removed duplicate. We handled missing values if there was any, right? So we were able to do that. Then we looked at the target column. We understand that the target column is actually what kind of imbalanced. So if it is going to be imbalanced, we did discuss, right, the methodology to overcome that. We spoke about sampling techniques. We spoke about weightage mechanisms, and we're going to be using the second one. And then, in fact, I think we went ahead and did our discussions on categorical variables. How do you handle them? So we understand that if there are categorical variables, you need to understand, if it is more than 15 categories, if they are probably more than 15 categories, using certain methodologies, you may have to reduce those categories, because high cardinal variables are typically preferred by predictive models like decision trees, even though they may not be the best, features here. Okay, so high cardinal variables are any day a problem for us. So removing them is actually speaking the right thing to do. And of course, for numerical values, also the same thing. For numerical values, you typically need to look at what is the distribution of these people. If it is a zero variance variable, you need to remove it. I think we did discuss about this one, the zero variance variables. Apart from that, you also need to understand if there are any extreme values. When I mean by extreme values, it means that it's basically your outliers. If there are outliers in the data, it's typically very good that if you can, kind of clip it, either remove it or sort of clip it. So what do I mean by clipping? You can see here, looking at this particular histogram of a variable, something like age, I see that most of the population are lying between 20 to 60, right? So a lot of people with 20, a very high number of people with 30, 40, and 50, then comes 55, 60, etc. So people between the range of 20 to 60, they are actually very high in numbers, and less than 20 or greater than 60, you see that there are very less number of people. They're probably outliers. So 20 to 60 is okay, but anything below 20 or anything above 60 is basically more of outliers. They are all extreme values. Hence, what we are doing is we are doing an operation, something called clipping. What do you mean by clipping? For any values above this particular upper limit, right, you will just replace it with this value itself. And for any value below the lower limit, you will replace it with the lower limit itself. Which means If there are any age values which are less than 20, they all will be kept as 20. And any age values which are above 60, they all will be made as 60 right now. So the moment I hit Control Enter, you guys can see, right? So now all the 70, 80, 90, all of these people have become a bar in 60. Can you see it? Right? So when you do a clipping operation, you're basically just kind of truncating the range. You're saying that, hey, I don't think these people should take up such a high value. I'm just going to replace those high values with a certain value I see to be nominal. So we are keeping 60 here as an upper limit and 20 here as a lower limit, and anything below and anything above will be made as these extreme values here. Right? Or another way of achieving the same thing is by doing this one. So one is np.clip will help you do it, or you can do it like this also. Say anybody above 60, their age values will become plain 60, and anybody below 20, their age values will become plain 20. So you can replace it. Now go back and check. You will have only people between 20 to 60. Similarly, as I told you all, looking at the variance of numerical variables is also a very important factor, because zero variance issue, basically you don't have to keep variables which are having zero variances. You can remove them. So these are some methodologies by which you can improvise your model by filtering out the unwanted variables or by cleaning certain variables if possible, right? So this is exactly how you can improvise your predictive model, by working on all of these variables here. Okay. So I think we have pretty much discussed everything, guys. We have spoken about categorical variables, how to handle them, numerical variables, how to handle them, right? So these are just more examples. I would just request you guys to go back and give a read about it. The same thing. I'm looking at the same, frequency counts. If it's too many in number, I would just like to cut it. Okay, so here you can see. So we have, extreme values and all. We're going to kind of cut it. Then marital status also we are looking at. So how is it working? So you may have some features that you can, bring from here. Similarly, looking at education, I see that there are a lot of education variables. I mean, categories. We can reduce them. So you can see here. We are saying basic 4-year, 6-year, 9-year. All the three categories, they are more or less like the same. Let us make it as basic is what we are saying. So you're reducing the categorical variables right now. Go back and check. You won't have the 4, 6, and 9. You will have only plain basic right now. So these are just more and more examples, guys. I would just request you guys to just go back and give it a small run. Just keep running it. You will understand what's happening. And now coming into the predictive model, suppose you're done with all these things where you've created your features, cleaned your features, everything. Now it's the time where you have to start creating your predictive models. Okay. So what we are doing is, as we always need, we're importing a logistic regression module, something that we have discussed, right? From scikit-learn.linear model, we are importing logistic regression. Let's hit Control Enter. He might have imported that library. Then the next thing that is important is this one. We have the function, something called train test split. I'll tell you what a train test split is. I think we might have discussed in our previous use cases, right? Anyway, so let me tell you what a train test split is. So we are going to import train test split function from this particular module. In scikit-learn, there is something called model selection. From there, you're importing the train test split also. Let's hit Control Enter. So these are the two things that we need for now, right? So I think all our data set, everything is done by now, correct? So let's go back and check our data. So I think our data set is all ready, right? So this is the data set that we have, our complete data set that was shared with us. Now, what do we have to do? We basically have to split them into capital X and capital Y. What is capital X? They're basically predictors. What is capital Y? That is basically your target. So you just go ahead and say, I want you to keep only the predictors and remove all the targets. Okay, that's what we're going to do next. So you can see here. So we're going back and saying capital X is equal to final data dot drop columns is equal to Y, which means drop the target column alone. The rest of the people will become a capital X, who are basically my predictors. Let's do it. Okay, so I'll use it as data. Okay. So capital X is done. So you can see here, your capital X is here. Similarly, now we are saying capital X of Y is basically my target. Okay. So sorry, data, right? So you can see here. So capital Y is going to be the target that we have. So we are saying data, this is my data frame. I want you to drop only this particular column. When you drop only the target column, the rest of the people are basically my predictors. And now we are saying, hey, I want only the Y column, which will basically be my target right now. So now what we can do is we can go back and say, hey, LM is equal to logistic regression. Then now we will do this one, lm.fit capital X comma capital Y. It's going to give us an error right now. So let's do it. Let's hit Control Enter. Giving us an error saying, hey, I was not able to convert a string value into a float. Looks like I met somebody like a failure. Okay, he has seen a variable where one of the value has been something like failure. He was not able to convert this failure, who's a string, into a float. So the problem is that, guys, when you look at the capital X, right, you have a lot of categorical variables with you, isn't it? So you have something like age, which is numerical, that's fine, but you have job, which is actually categorical. Then you have something like education, which is categorical, marital status, which was categorical, right? So the string values as such is something that your predictive models cannot understand, right? Hence, what we're going to do is we are going to convert them into something called as factors. I think all of us are okay with our programming, right? You should have come across something called factors. What do you mean by factors? Instead of having categories like A, B, C, I will just give them numbers like 1, 2, 3, right? So what is the factor variable actually doing? He's saying, hey, instead of having it as a character variable with all string values, we can just convert it as numbers like 0, 1, 2, 3 goes on. Hence, what we're doing is, guys, we're going here at the top. In Python, from scikit-learn.preprocessing, there is a function, something called label encoder. Okay, there are two methodologies to do it. I'll tell you both. I'll tell you why you need to use this one. Okay. So we're basically coming up with something called label encoder. Okay, so we are saying, hey, I want you to import something called as label encoder. Then we are saying, hey, create a label encoder object, which is equal to the label encoder function. Let's hit Control Enter. Now what you can actually do is, you can just go back and select only the categorical columns. Okay, so I'll just go back and say, hey, data, I want you to select only the D types. That is the data types of columns. Whoever is an object data type. Objects are basically categories. So we are saying, hey, data, I want you to select the D types, that is the columns data types, which are basically objects. Let's hit Control Enter. He gives you all the column names right now. So these are the people: job, marital status, education, default, right? Month, days of week, previous outcome, everything. All of these people are categorical in nature. Now what we will do is, we'll go back and fetch only the categorical columns for us separately. You can see here, we have fetched them separately. Now what we are going to do is, guys, we're going to say, hey, label encoder, I want you to go back and fit and transform on each and every column. So what are you saying? You're saying, I want you to fit and transform on each and every column. So it's like this. So you're saying label encoder, fit and transform. Let's say I give my capital Y, okay? What is a capital Y right now? Yes and no. When we hit Control Enter, yes and no will basically become 0 and 1, right? So it's taking up each and every level and it is encoding with numbers. That's it. So it takes up a categorical columns. It'll find what are the levels on the inside, and for each and every level, it's going to basically keep as a numerical value here. That is exactly what a label encoder is doing. So as per alphabetical order, N comes first and S comes next, isn't it? So what will happen is, for N, no, he will give 0 as a value. You guys can see it. Yes comes later, hence he is taking 1 as a value. So based on the alphabetical order, it's going to find what are the categories. And for those categories, he's going to basically give numbers like zeros and ones. Okay. So what we have done is, we have done it for a single column. How can I do it for every categorical column? In pandas, we have a function called apply. The apply is basically going to iterate over each and every column, and he'll apply a function for us. So we are saying, hey, these are the categorical variables. Can you iterate over each and every variable and apply this label encoder? Sure thing, of course. So he's able to do it for us. Now we will just store it in the categorical data columns. We'll fetch the numerical columns also separately, and then we will concatenate them together to become a final data here. So let me go again, guys. I think all of these things I can just remove it. So see here, let me go again. We're importing logistic regression because that's a predictive model we're going to create. We're importing train test split because that's a validation method we have. We're importing label encoder because categorical columns cannot be used directly. They need to be encoded with numerical values. So we're importing all the three packages here. Then we are saying, hey, label encoder is equal to use this label encoder function. So it will create an instance of label encoder type. Then we are saying, hey, data, I wanted to select only the object columns for me, which are basically categorical columns, right? And then what we're going to do is we're going to go back and say, hey, I want you to give me the column names. I'll choose the column names for now. So we're keeping the column names for now. Then what we're doing is we are creating a numerical data set by saying, hey, remove all the categorical columns. The rest of the people are numerical in nature. Then we are saying the categorical columns will be another piece. The categorical columns will go through the label encoder. You get the final data set here. You have the numerical data set with you here. Let us merge the people together to get the final data set here. So basically you split them into two, numerical, categorical. Categorical alone got treated. Then once again, they got merged together to become the final data here. Now what we will do is the same thing that we discussed. So we'll just go back and say, hey, from the final data, I want only the column Y, which will become my capital Y. The rest of the people will become my capital X, my predictors and targets. Now we can create a predictive model using the entire data set. We're saying, hey, all the 41,176 records needs to be used to create the predictive model. Let's hit Control Enter. He gives you no error. Looks like perfectly he was able to predict. Now what are we doing? Sorry, he was able to create, not predict, okay? He was able to create. Now what we're doing is, we are telling him, hey, can you predict for the capital X itself and give me what are the predictions you are coming up with? He says, hey, these are the predictions I am coming up with. But we already have the true value also with us. So what we're doing is, guys, the 41,176 rows that we used, right, for the creation of the model, the same data set which was used in the creation of the model, we're using it for testing purpose also. It is basically something called as in-sample testing. The name is something called as in-sample testing. It is one of the simplest validations you can do. Why? Because a predictive model that you've created who's not able to perform very good on the data on which he got created itself, right? Such a predictive model is surely not a very good thing to use. You get what I'm saying, right? So a predictive model that you're creating, right, is not a good predictive model if he's not able to perform very good on the data set on which he was created itself. So you're saying that, hey, I trained you with 1 or 2 books, right? So your exam is now, your exam questions are coming from the same books itself. If you're able to answer, it means yes, you've learned properly. I don't have to ask questions which is out of the syllabus or coming out of some other books. So we are doing something called in-sample testing. On the training data set itself, we are asking for, hey, can you give me what are the predictions? He gives you the predictions here. What can we do? We have the true value capital Y with us. Now we can just go back and check. Okay, so for how many people do you think you have correctly predicted? So he's giving all trues and false. Let's do a sum of it. He'll tell us that, hey, for 37,479 people, I did predicted correctly out of a total of what? 41176. So you have got an accuracy of 90% for what? For an in-sample testing here. So we have got an accuracy of 90% for an in-sample testing right now here, right? This is basically an in-sample testing where the data set on which the model was created itself is being used for the testing purpose. While here at the bottom, you guys can see, we are creating train test splits. I hope we have discussed this one, but quickly let me just draw the diagrams for you all. So you can see here, this was the main data set we had. We split it basically vertically to create the capital X and capital Y. So this was the capital X, all the predictors. This is the capital Y, the single target. Then what are we doing? We're going to create a split somewhere here. And then we will say, hey, this is 80% of the total data set to be used for the training purpose. This is 20% of the total data set to be used for the testing purpose. So this will be called as train underscore X. He will be called as train underscore Y. He will be called as test underscore X, and this guy as test underscore Y. So you have train X, train Y, test X, and test Y. So you'll say, hey, this is the predictor for the training data set. This is the target for the training data set. Create a model using both the people. Now you will say, hey, pass on this guy as an input. Give me the prediction, which is Y predicted. I will compare it with the true value and find what is the accuracy. But the best part is this 20% was not used in the creation of the model. While in the previous case, what happened? The entire dataset was used in the model creation and the entire dataset itself was passed as an input. So here we are not doing like that. We are just doing it, the opposite fashion. We are saying, no, I'm going to keep a little bit outside. That little bit of data set kept outside is going to be used for the validation purpose here. So let's go back. You guys can see here, we have a function, something called train test split. We are saying capital X, capital Y, give me X train and X test. Capital Y, give me train Y and test Y. Test size is 30%, which means train size has to be 70%. Logistic regression model, only on the training data sets, predictor and target. Come up with the prediction for the testing data set. Then what are we going to do? We're going to go back and check it with the testing data set's original value, which is Y cap. Check if it is equal to Y underscore test. Let's hit Control Enter. So sum of this particular guy is equal to what? 11192. So 11192 people were correctly predicted out of 12353. Let's hit Control Enter. You got a 90 right now. Looks cool, right? Got a 90% accuracy for out of sample testing. So where you basically kept a small sample outside for the testing purpose. It's called as an out of sample testing. So the out of sample testing has given us what? 90.6% of accuracy right now. Good. So for in sample, I got 91. For out of sample also getting 90 is a very good thing actually. So the predictive model is able to relate on why certain customers have responded and why did not certain customers respond here. He's able to kind of connect the dots here, right? So this is exactly how you create a predictive model, guys, to come up with, the predictions for the is going to work. Now, what will you do tomorrow? You'll basically give some inputs for him. Say for an example, let's say the testing data set itself, okay? LM dot predict X under test. So tomorrow I got a new set of customers. I need to identify who of these guys should be selected for the campaign. So you're predicting here. So wherever there is a 1, you'll choose all those people. Wherever it's a 0, you'll not run the campaigns on those people. That's all. Or if you want only top 100 customers or something, you will predict for probabilities. And then you will find who is having the highest probability. And that highest people will be basically used here. So you can see here, this guy is having 87% probability of responding. So he might be in the top 10. We never know. Probably another guy might have 89%. So he might also be in the top 10. So find who is having the highest probability of responding right now, and then you can shortlist the top 50, the top 100, everything. Okay. So then using probability, you can come up with the probability of responding, and using that probability, you can just sort them in a descending order fashion, choose the top 50 or the top 100. That's it. So this is exactly how you do it, guys. Actually, there are a little bit more scientific methods like using lift charts and gain charts, and evaluating how the predictive model works. Then even choosing the top decile of people and all. There are a lot of other small techniques available, but in the interest of time, let's move on to the other topics. Probably another day we can just revisit on all those things. It's all part of model evaluation procedures. I think we have a separate class for it. There we can discuss about it. Lift and gain charts. How do you use them to evaluate if your predictive model is good or bad, right? And how can I choose a top set of customers? So you can divide it at deciles, like 10 portions. Then you can decide whether the top 2 portions have to be used or the top 3 portions have to be used. So that's what is called as a decile analysis. So we can in fact do a decile analysis, but probably in another class. Okay, let's take one step at a time here. Yes, so now tell me, guys, is it okay? Are you all able to follow this use case on how did we solve it, etc.? Right, so how do you treat all the predictor variables? How do you use them in the predictive model? How to create the predictive model, a basic evaluation, train test split, looking at a metric, something like accuracy. Clear? Okay. Okay then. So I think with this, we can kind of close this use case. Okay. There are a couple of more things, as I told you, in the interest of time, let's take it pretty slowly, towards the end or something. We just need to move on to the other topics. It's a compulsion for us. So let's just jump into those. Okay. So if there's no questions still here, I think we can jump on to the next topic, which is basically decision trees. Okay. Just give me 1 second, guys. Okay, cool. So the next topic that we're going to be discussing is something called decision trees. Okay. So starting from this topic onwards, for another 3-4 predictive models at least, guys, they are all completely connected. Okay. Like decision trees, random forests, bagging, boosting, all of these topics are pretty much connected to each other. Okay. They have a lot of dependencies on each other because by the end of the day, they are all decision trees for us. Okay, so there's a lot of continuity for all of these topics. So there's going to be a lot of connection also between them. So the next predictive model that we're going to be discussing is something called as decision trees. Okay. So what exactly do you mean by decision trees? I'll tell you guys, decision trees is a beautiful class of predictive model. Okay. It is more like it's a off-shelf kind of a model. It's a predictive model which is not so similar to any of the predictive models that we've discussed till date. It's a completely different kind of a predictive model. I tell you, starting from clustering onwards, right? It's your machine learning. Anything before that, it was all it was all statistics. So take up linear regression. What happened? You derive coefficients. Take up logistic regression. What did you do? You derived the coefficients. Look at naive Bayes. What did you do? You came up with probabilities. Look at clustering. Do you think the model estimated something? I mean, he just gave you a prediction, right? Did he estimate some kind of a parameter or something on the inside? Doesn't seem so. In the same class of model, you have decision trees who's not very statistical in nature, I'll tell you. It's more of a machine learning in nature. The reason because there are something like parameters that are getting estimated here. It's not completely true, by the way. There are certain decision trees where certain scores and etc. are getting estimated. But I'm saying 90% of decision trees, they don't have any kind of a parameter estimation that they're doing. That is why models like these people are called as non-parametric models. They're called as what? They're called as non-parametric models. What do you mean by non-parametric models? These are certain models which doesn't have any sort of an assumption. So say they don't assume that your data is probably something like that, which they can use it. Or they don't create certain parameters and other things or coefficients like what linear regressions or logistic regression model would do. Decision trees are basically non-parametric models here. They don't estimate anything. They don't come up with something like coefficients that can be used in a sort of an equation, nothing like that. It's just by the end of the day a couple of rules, that's it. So we call decision trees as a non-parametric model. That is number one. The second point that you all need to understand about decision trees is it is a non-linear predictive model. Okay, so what do you have? It's a non-linear predictive model. Unlike the example like a linear regression, where the name itself is telling you that it's a linear model, or let's say somebody like logistic regression who is actually speaking what? A linear model, small extension, who's also once again a linear fashion. A decision tree is somebody who's actually strictly non-linear in nature, which means if you give a linear data, right, a decision tree is somebody who's not at all suitable, and a simple linear regression itself would have done a very good job here. But when you give a non-linear data, right, decision tree is some person who can work pretty beautifully. Once again, conditions applied, and somebody like linear model is going to flunk pretty badly here. Okay, so there are several other models, guys. Say for an example, there is something called bagging, boosting, random forest, neural networks. We do call them as a non-linear model only. But unlike the case of decision trees, right, they can work on linear data and still give you good predictive powers. Yes, even though it's a non-linear model, they can work on linear data and they can give you good results. But somebody like decision tree, it's not so. I'll tell you why it is like that. Okay, I'm going to discuss why it is not going to work so good on a linear data. Okay, but as of now, just understand that he's more suitable for a non-linear data and 0% suitable for a linear data. So it is a strictly non-linear predictive model that you should be following. Okay, so what are decision trees? Decision trees are more like an off-shelf kind of a predictive models, guys. They don't have any sort of a similarity to any of the predictive models you guys might have seen previously. It's called as a non-parametric model. The reason because they don't estimate any sort of parameters on the inside. And it's also a pure non-linear model. Why? Because they work very good on non-linear data set and they flunk pretty badly on linear data sets. Okay. So why is the reason, if you think so? It's pretty simple, guys. I'll tell you the basic ideology behind a decision tree. What exactly is a decision tree trying to do? So the work of a decision tree is pretty simple. Okay. He is going to basically populate your entire data set. Okay, let me call him as something like a root node. I'll give it as a name. As the name says, he's creating a tree. Okay, he's creating trees using decisions. He's going to create a inverted V-shape kind of a tree, top-down approach, many other keywords to follow. So he's populating all the data points here in what is something called as a root node. And then what is going to happen is he's going to go back and split this particular root node with all the n number of members, and he'll start creating smaller subsets. So what is he actually doing? He's actually creating smaller subsets. So say for an example, you had 100 data points here, okay? He says, okay, I can have all the 100 data points, but I see that there is a lot of heterogeneity. So what's happening? There's a lot of heterogeneity. I see that all of these people are not so similar to each other. There's a lot of dissimilarity. Hence, we are saying, okay, why don't you use a split? So say for an example, assume guys, there are 1,000 people standing in front of you. What is the simplest methodology by which you can divide the 1,000 people? You'll use gender, right? So you'll say, okay, all 1,000 people, I think there's a lot of heterogeneity. So let me use a variable something like gender, so that gender is equal to male, let them come on the left hand side. Gender is equal to female, let them go onto the other side. So what you might end up with is, let's say n is equal to 55 here and n is equal to 45 here. So what happens is, compared to the 100 people that you had previously, where there was a lot of heterogeneity, now the heterogeneity is going to reduce a little bit at least. So what is going to happen? The heterogeneity is going to reduce a little bit at least here. So the work of a decision tree is pretty simple, guys. He is going to basically start using a lot of decision splits, and he'll keep reducing the size of each and every subset, or he's going to keep creating smaller subsets which are more and more homogeneous in nature. So what will happen? It will become more and more homogeneous in nature here. So lesser heterogeneity, more homogeneity. He's basically going to start grouping people which are all very similar in types here. You may actually try to connect it with the clustering example that we have seen. So you might ask me a question. So didn't the clustering do the same job, where he was trying to find similar people and group it? The difference is, clustering was unsupervised, but decision is a supervised learning model. So what do we have? Clustering was an unsupervised learning model, but decision trees are supervised learning models, which means they don't just need capital X, but they also need a capital Y. Only then they can relate with the capital Y and understand whether it is homogeneous or heterogeneous. So decision trees are supervised learning models. They are non-parametric models. They are non-linear predictive models. And another very important point is, they are people who are capable of doing both classification and regression. So decision trees, methodology can be tweaked a little bit to solve both the problems, both a classification as well as a regression. And the work of a decision tree is basically to keep dividing a massive data set and keep creating small individual homogeneous subsets. So the ultimate goal of this guy is to create small subsets which are more and more homogeneous in nature here. Okay. So I start off with a giant data set, then I divide it into two. Those two will get divided into another two. Those people will get divided into another, let's say 8 or something. It keeps happening over and over and again till you end up with small subsets by the end of the day. So this is the role of what is something called as decision trees. They basically try to create small subsets. So before I deep dive into this algorithm and I tell you, how exactly it works, how the predictive model is getting created, how the predictive feature comes in place, let me first clear you all the reason on why it is so beautiful on why is it so beautiful on a non-linear data, doesn't work much on a linear data. Let's solve this particular question, shall we? Pretty simple, guys. So say for an example, let me assume we have a data set, okay? So I have my X variable and I have my Y variable, okay? So let's say for an example, I have a lot of data points with me, okay? So I'll just create a lot of data points, okay? So what a decision tree will actually do is, he's actually dividing a bigger data sets into smaller data sets by using certain criterions, using certain conditions, correct? So what did he use here? He said, hey, gender is equal to male and female. This is one criterion, okay. Next, what he might have used something like age. So age less than 18, age greater than 18. This is another criterion he might have used. Then he'll say, okay, greater than 18, he might have later on asked, saying, okay, so people having an income, something like less than $10, greater than $10. So at each and every subset, he's just keeping a lot of decision splits. So say for an example, guys, decision trees, right? They see its popular usage in something called scorecard development. Okay, something that all of us can connect to. Scorecard developments. In banks, you create scorecards, right? There scorecard developments, decision tree, see its usage a lot. So what happens is they'll basically ask the question, okay, I have this customer. What is his, let's say, FICO score or a CIBIL score? Okay, he's got a FICO score of somewhere like 700. Okay, it's good. Then you may probably say, okay, what is his age right now? His age is probably 25. Okay, it is good. So what is his income? He is earning only $2. Then you'll say, okay, don't give him a loan. So what's happening? You're basically saying, okay, these are the people who might default. These are the people who might not default, or people who will have difficulties in paying, people who may not have difficulties in paying. So you want to kind of segregate the two populations. So now you're saying, I have a single population. They have all the people who will have trouble paying and no trouble paying. All we are doing is we are asking a decision trees to separate them out. So say decision tree is saying, okay, I can just separate them out. You know, you have given me the entire data set. I can just separate them out saying, hey, these are the people who will have trouble, while these are the people who will not have trouble. That's all, right? So what you're basically doing is that you're basically trying to segregate all of this population here using certain decision rules, right? So I think there's a question online. Could you please provide an example on linear data versus non-linear data or variable? An example on what is linear and non-linear? Okay. Okay. So what is linear? See here. Basically, a straight line trend is something called as linear. So let me give you an example. Did you guys go through your statistics sessions where you might have discussed correlation, covariance? No? Yes? Sorry, just give me 1 second. Okay. Okay. Now see here, guys. So these are two variables. Okay. So you have a variable. So you have a predictor capital X and you have a target Y. The same X and let's say same Y. Okay. You're creating a scatter plot. Okay. There are a lot of data points. You're creating a scatter plot. This is how they are actually in a line. Whereas here the scatter plot, the points are all something like this. So when I connect them, they are more on a curve linear nature. So I'm saying this is a linear data and this is a non-linear data. I'll tell you why. Very simple. So this is some value of X, isn't it? So let us assume here X value is equal to 5. What is the Y value? Y value, let us assume it is 10. Okay. So X is equal to 5, Y is equal to 10. Now let me keep X value to be 10, Y value will become 20. So X is equal to 10, Y is equal to 20. Then let X become 15, Y will probably become 30. X equal to 15, Y is equal to 30. In the same stage, 20, 25, 30. So X is equal to 30, then Y should have basically become what? 60 here, isn't it? So see here, guys, compare your delta X. Delta X is what? 5 units. What is your delta Y? 10 units. Compare these two people. Delta X is 5 units. Delta Y is 10 units. So everywhere when you compare, for a certain value of change in your X, there is a fixed value change in your Y, isn't it? When your X changes by a certain value, your Y is changing by a fixed value. From 5 to 10, 10 to 15, 15 to 20, I'm not worried about what is my starting point, what is ending point. By the end of the day, if the difference is 5 units, my target will increase by 10 units. This is basically a linear data. Whereas in a non-linear data, see here, let's ask the same question. So let's go back and ask the same question. Okay, your probably x is equal to 5 right now. Now then your x is equal to 10. Then you become 15, you become 20, you become 25, 30, 35. So x is equal to 5, x equal to 10, x equal to 15, x is equal to 20, x equal to 25, goes on up to x equal to 30. We look at the y value could have been 10. Then y value would have become 25. Then for 15, it could have become stagnant like 27. Then it would have probably come down to 20. Then it's going to 15, then it's probably going to 0. So what do you see here? Delta x is still 5 units, delta y is 5 units, but between these two people, delta x is 5 units, but delta y is only 2 units. That is, for every change in one variable, if there is a proportional change in the other variable. So I'm telling you, right? So I'm giving you $5, you get me 10 chocolates. I give you $10, then how many chocolates will you give me? 20 chocolates, right? So there is a proportion involved. It is all proportionally involved. While here it is not so. Here for every change, the change is going to be different. So you said $5 would have given you 10 chocolates, but for $10, if you tell me that I'll get only 17 chocolates, then it's a problem for me. Then for $15, if you tell me that I'm going to get only 24 chocolates, then once again it's a problem for me. So for every increment in the x, the y should increment in a certain constant number. If it doesn't do it, then it's a nonlinear data. If it's happening, then it's a linear data. Okay. So a straight line trend is typically a linear data. You typically use people like covariance and correlation to estimate how much of linearity is present in this particular data. Right? That's how the formula has been designed. So it will help you find the linearity, the relationship between two people. But what relation? Linear relation. Let's please understand that. Two variables might be related, but covariance or correlation might have come down. Why? Because the two people might have been inversely related. Sorry, non-linearly related. So covariance and correlation, please underline it. It's a linear relationship. They are people who can help you understand linear relationships between two people, two variables. Okay, great. I think after a long time, I'm getting some question at least during a class. Okay, good. Thanks. Thanks, guys. I was wondering, for the last few classes, I heard no questions, nothing. Is it that things are over the head? Feel free to tell me, guys. Feel free to stop me then and there where you're not able to follow. You know, if in case you want me to repeat it also, feel free to tell me. Okay. Great. So going back here, we were talking about the decision trees. Decision trees, supervised learning models, non-parametric in nature, non-linear models. They can do classification and regression. Their task is basically to keep recursively dividing a massive data set into small subsets. They work good, but with conditions applied. I'll say occasionally good, doubtfully good on a nonlinear data, but they surely are going to flunk on a linear data. I'll tell you why, guys. Look at this case, you have 55 members, okay? Assume this is your X and this is your Y, okay? I've plotted 55 members here. Let's assume like that. We're keeping a variable something like age and we are deciding. We are saying, hey, age value less than 18 is one group, age value greater than 18 is another group. Okay, so X variable is what? Basically your age. So you have 0, 1 till goes on till 100 age or something. Where is 18? 18 is somewhere here. Hence, what you're doing is you are creating a decision split right now. So I'll just go back and create a decision split on this particular data set, something like this. So what have we created? We have basically created a simple decision split right now. Just give me a second, guys. So this is a decision split that we have basically created, right? He's saying people on the left-hand side is of one type and people on the right-hand side is of another type. Okay. Then he's saying people on the right-hand side who are values above 18, use the income variable and split them further. So let me assume this is income variable. He's saying income above $10 and below $10. So let's assume $10 is here. I'll go back and create another split, probably horizontally, something like this. So we'll go back and create a horizontal split, something like this. So previously we had a vertical split. Now we are having a horizontal split. So this was your vertical split that we had previously. This is your horizontal split. So this is decision split 1. This is decision split 2. So who are these people? This node, people whose age value is less than 18. It is all of these guys. All of these guys are group number 1. Then he's saying the group number 2 is greater than 18, but there is a further division, which is less than 40, sorry, less than 10 and greater than 10. So you're basically saying, okay, this is another group that I'm creating. Okay. Similarly, we're going to go back and say, hey, this is another group that I'm creating. So what did you end up with? You basically end up with 3 groups. So this is your G3 and the previous guy was basically your G2, isn't it? So this entire portion becomes your group 1. This bottom portion becomes your group 2. This upper portion will become your group 3. So what are you basically doing? You're keeping a decision split something like this. So you're saying, hey, I need a decision split something like this guy, and I need another decision split something like this guy. Look at them. Are they not at 90 degrees to each other, the 2 decision splits? Here he's saying age value less than greater than 18. Here he's saying income value less than greater than $10. So if you look at the 2 decision splits, they are at 90 degrees to each other. So in this fashion only, you can see they are creating non-linear decision boundaries only all the time. Can you see it? So this what? This is your group 2, isn't it? What is a boundary? The boundary is something like this, the dark blue line that I'm drawing just now, right? This is the boundary for that guy. What is the boundary for G3? This dark blue line that I'm just drawing. So all the boundaries, if you see, they are all going to be some boxes and all something like this. The boundaries are all going to be at 90 degrees to each other. That is why we are saying decision trees are basically people who will create orthogonal decision boundaries. Let's please keep up with this particular keyword. Who are decision trees? Decision trees are people who can create orthogonal decision boundaries. Basically, they will create decision boundaries which are at 90 degrees to each other. So the first decision split and the second decision split are at 90 degrees to each other, isn't it? They're basically orthogonal in nature. So decision trees are basically people who will create orthogonal decision boundaries. The decision boundaries are going to be 90 degrees to each other. And since they are at 90 degrees to each other, since they are all completely non-linear, since they are all basically, orthogonal, you can see that it can work on a linear, non-linear data beautifully. But if it is a linear data, he may not be able to work it out. So at any time, whenever the decision splits are made, it's always orthogonal. It is always a non-linear decision boundary. There is no chance he can create a linear decision boundary. There's no chance, except if you say there is only one split, something like this. I mean, one split, something like this. The moment you make a second split, that's it. It's non-linear, right? So this is a guy who will always create only orthogonal decision boundaries, guys. What are orthogonal decision boundaries? They're basically decision boundaries which are at 90 degrees to each other. So all the decision boundaries are going to be 90 degrees intersecting, orthogonal in nature. Since they are orthogonal in nature, the decision boundaries are always going to be non-linear in nature, more suitable for non-linear data and not so suitable for linear data. So this is why, I keep repeating, saying that decision tree is more of a non-linear model, more suitable for non-linear data set and not very suitable for a linear data set. In fact, as I told you, it's conditions applied. We even have an assumption saying one decision tree model may not be an enough predictive model, may not be a very good model. Okay, so typically we create many decision tree models, 5, 6, 7, 100, 1,000, 2,000s. So that is when it gives birth to something called bagging, boosting, random forest, all of these concepts. So there is a general assumption that a single decision tree model also may not be so wise enough. You can make the predictive power better and better the moment you start creating more decision tree models. But I'll tell you, still in most of the cases, one decision tree models will do the job. But always, it's good that you go with the conditions applied factor. It may not be very good all the time. If it's going bad at some cases, just go back and create many decision tree models and combine the predictive powers coming from all the decision tree models. That's it. Okay. So decision tree models, supervised learning models, non-parametric in nature, non-linear in nature, classification and regression is something that they can do. It's a orthogonal decision boundary that he's going to create, which is more suitable for non-linear data, very less suitable for linear data. The work of a decision tree is basically to keep splitting a massive data set into small individual homogeneous subsets using certain decision splits. So what you end up with is say for an example, if I have a massive population like this with both the kinds of classes, that is troubled loans and non-troubled loans. So this guy will help you separate the population out. So you'll say these are the people who are troubled and these are the people who are not troubled. He can help you separate the two populations here. Defaulters, non-defaulters, respondees, non-respondees, or even for a regression case, he can just split it out. So sales with less value, sales with greater value, anything, whatever it is. He can split out the data sets based on the similarities between them. That is the work of somebody called as decision trees. And please understand, it may have a little bit of similarity with clustering in terms of its objective, but it's not so because clustering is an unsupervised model, while decision tree is a supervised learning model. So that's a minute difference between what a clustering is trying to achieve versus what a decision tree is actually trying to achieve here. Okay. Yes. Are you all able to follow till here, guys? Any questions till here? Is everybody convinced till here? All these points that we've just discussed? Yeah, clear? Okay. I didn't hear it from Hassan. How about Rakesh, Ravi, Sanjay, Anu? Okay. 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 So before we jump into the core objective of what a decision tree will do and how is he getting kind of created, let us first understand a couple of elements that you have to understand about a decision tree. Okay, there are a couple of elements, or let's say certain names you'll have to keep up with, or terms you'll have to keep up with a decision tree. So if you see a decision tree, right, it's typically created in a top-down fashion like this, right? It's a inverted V kind of shape is what he will take mostly, isn't it? So in a decision tree, the very first node at the very top that you see, right, where he will basically contain all the data sets, he is called as somebody called as a root node. So what is he? He's basically somebody called as a root node. What do you mean by a root node? The root node is basically the person who will have all the data, entire data set at the first position. Then further is where you'll start dividing him. So root node is basically the person at the very top. So if you ask me, are there any incoming connections for him? The answer is no. But are there any outgoing connections? The answer is yes, because he's splitting himself and he creates two or more daughter nodes here, right? He's creating two or more daughter nodes. So there are outgoing connections, but there are no incoming connections. So this is the work of a root node. Then what you will have is you'll have somebody called as internal node. Example is this guy here. He is an internal node, or sometimes we also call it as a decision node and all. But there's a lot of what I would say is overlap between these terms. So please don't use a decision node. Let's keep up with an internal node. An internal node is a person who will have incoming connections and will also have outgoing connections. Finally, over to these people, at the very last, you have something called as leaves or leaf nodes. They are people who will have incoming connections, but surely no outgoing connections. So you have 0, 1, 1, 0, and 1, 1. Obviously, you can't have 0, 0, which means you have not yet created a model at all. So you'll have a root node, you'll have an internal node, you'll have a leaf node. And the leaf nodes are basically the area where you'll start making predictions. So leaf nodes are basically the areas where you'll start making predictions. You'll come up with predictions. So you will say that, hey boss, I think this subset is being dominated only by the troubled loans. These are people who are not troubled loans. So whoever is satisfying all of this criterion, tomorrow you'll say that they'll have trouble paying the loan back. But these people, they may not have trouble in paying the loan back, right? So based on a historical data set, you'll kind of subset, you'll come up with the criterions on what made you kind of make this individual subsets. And tomorrow also, if these criterions are getting satisfied, then you will be able to come up with predictions saying, hey, I think this criterion has got satisfied. So I think this is the prediction you need to come up with. So the predictions are all going to happen at the leaf node all the time. Okay, so you have a root node, you have an internal node, and then over to something called as a leaf node. So these are the three parts that you need to understand. And then there is a decision split. So whenever you split it, right, saying, hey, gender male and female, age less than greater than, or let's say, account balance greater than less than, or let's say monetary value like greater than less than. So whatever you do it, those are all something called as decision splits. When you're splitting a node using certain decision and you're splitting two or more, when you're creating two or more nodes, that is what is called as a decision split. Okay. So these are the basic keywords that you'll have to first understand the structure of a decision tree. You have a root node, you have an internal node, and then over to something called as a leaf node. Okay. So now talking about the induction of a decision tree. How does a decision tree basically gets created? What is the objective of creating a decision tree? What is he ultimately trying to help us solve? So induction of a decision tree is the next topic that we're going to be discussing, guys. So let me tell you all something. The decision trees that you see, right? All of these decision trees, algorithms today you have a lot of models, guys. So you have something called CART, C-A-R-T. It's called classification and regression trees. There is something called C 5.0. Previously, there was something called C 4.5 that people were using. Then you have something called CHAID, C-H-A-I-D. It's called chi-square automated interaction detection. So there are several other kinds of predictive models. Okay, RPART, recursive partitioning. I think it's a CART model. So just another type here under the CART. So there are different kinds of predictive models that you can create, guys, under the decision tree. There are different authors. They follow different methodologies. Okay, CART, C 5.0, CHAID. They just have small changes here and there. I'll tell you what are the small changes here and there. But the way by which all of these guys are getting created, right? The original algorithm or the original framework is basically something called as Hunt's algorithm. Okay. For the induction of decision trees, the original algorithm was basically something called as a Hunt's algorithm. Okay, so the Hunt's algorithm is one of the first algorithm that was created. It was used in the creation of a decision tree, something called ID3. Okay, ID3 was one of the very beginning models that people created. ID3. I think it's called interaction detection 3. I don't know. So interaction detection 3 or ID3. Then came C 4.5. Then came 5.0. Then came CART. Then came CHAID. There are different kinds of decision tree implementations available tomorrow, but Hunt's algorithm is mostly the base for all of this induction processes. So what does the Hunt algorithm actually tell us? Very simple, guys. There are a couple of steps you all need to understand in the Hunt's algorithm. Okay. So what this guy told us is, he said, hey, the very first thing that you need to do is populate all the data points in the root node. So what are we saying? We are saying, hey, I wanted to populate all the data points in the root node. So what did the Hunt's algorithms tell us? He said, hey, go back and populate all the data points in the root node here. Then what this guy said is, he said, go back and evaluate how much of heterogeneity is present in this particular data set. When I mean by heterogeneity, see you guys, let's go back to the response models that we created, okay? We had two labels. We had customer responding, we had customer not responding. Let us assume there are 50 people who are responding and there are 50 people who are not responding. It will become 50% and 50%, right? I'm calling this case as a highly heterogeneous case. I'm calling it as what? I'm calling it as a highly heterogeneous case. Why? Because very simple. See guys, let us assume you have a region something like East, okay? Let's assume you have a region something like Central. So in this region, I see fraudulent claims and non-fraudulent claims, okay? There are 50 people who came up with fraudulent claims, 50 people with non-fraudulent. Here, 10 people came up with fraudulent, but 90 came up with non-fraudulent. Then let's go to West. West is basically 90 and 10. So what are you doing? Let's look at Central. The distribution is 10 and 90. So there are a lot of people who are making non-fraudulent claims. So what is the decision you will make here? You will basically say, I think most of the people coming from the Central region are people who will not make any non-fraudulent claims. Sorry, who will make only non-fraudulent claims. They are the people who will not make fraudulent claims, or they are the people who will, come up with non-fraudulent claims. Whereas in the West region, the distribution is 90 and 10. So the decision is basically that any people or any profile or any customer you are originating from the West region, right? They are most likely to make a lot of fraudulent claims. So you need to go back and deep dive. The underwriting team has to make sure that they don't make any sort of a mistake. Well, look at the East region, guys. It's 50-50. What sort of a decision do you think you can probably make when it's 50-50? Do you think I can call them as, no, all the people are going to be fraudulent? No, there are equal number of non-fraudulent. Do you think I can say they're all going to be non-fraudulent? No, they're going to be equal number of fraudulent claims also. So these are the cases where I'm not able to make any kind of a decision. Why? Because it is equally dominated by fraudulent as well as non-fraudulent cases. That is why here we are saying that the heterogeneity is pretty high. It is pretty massive. I'm not able to make any kind of a decision because I see 50-50. The heterogeneity is massive. I'm not able to separate out the two populations right now. But here what has happened? Somebody was able to separate out. After separating, there's only 10 and 90. He was able to separate a lot of fraudulent claims outside. So now there are only 10 fraudulent and 90 non-fraudulent in this total. Here what happens to the heterogeneity? It's actually pretty low, isn't it? Because what do you see? You see that 10 people are only fraudulent, but 90 people are non-fraudulent. So the heterogeneity has basically come down. Now I can make a clear decision. Even here, the heterogeneity has come down. Here it's only 10 and 90. So this is a node where the heterogeneity is at its maximum. Here the heterogeneity is all lower. So basically, guys, when I mean by heterogeneity, right? In regression, it's a different method. Let me talk about classification for now. Okay, let's just assume that decision trees for now are classification type. So we are basically doing what? We are looking at the distribution, guys. That's it. If the distribution is uniform means what? They are almost same. Then heterogeneity is very, very high. Or else if it has been skewed something like this. So one guy is very high, another guy is low. this guy is low and this guy is high. In these cases, you will say that the heterogeneity is lesser. So what happens? The heterogeneity gets lesser. So skewed distributions are something that we want, whereas uniform distributions are something that we don't want. We want to basically get rid of those. So what the Hunt's algorithm, this guy told us is, he said, hey, let's go back and populate all the data points in the root node and let us evaluate how much of heterogeneity do we have. If it is already highly homogeneous or it is having the least heterogeneity, right, then what will happen? Root node itself will become the leaf node. That's all. That is the final thing. You are not going to split anymore. You're saying what? If heterogeneity is literally equal to 0, if heterogeneity is equal to 0, the root node itself will become a leaf node, is what we are saying. Else what will happen? You're going to say, okay, go back and start the splitting process. That's all. So this is the first check that will happen, guys. I'm going to populate all my data points into the root node. The question is, okay, this root node, is it all heterogeneous or is it homogeneous? If it is going to be, heterogeneous, then we are saying, okay, I need to probably start the splitting process. While the opposite, if it were completely homogeneous, then we are going to probably say, okay, I think the root node itself can turn out to become the leaf node. I don't think I need to do any more splitting further. So the splitting process is something that is not even going to start here. It's not even going to begin. So this is the very, very first check that will happen, where the root nodes are getting populated, right? And then you're checking what is the homogeneity, heterogeneity and all. Based on that, you decide whether you need to start the splitting process or you don't want to probably do it. This is the first thing. Now, suppose in case, guys, you're saying, okay, I found it to be heterogeneous. By the way, guys, I'll tell you another thing. How to evaluate and quantify the heterogeneity. There are certain measures, okay? I'm going to talk about the measures in some time, but let me just kind of give you the names of those people. There are certain measures who will be used in evaluating the amount of heterogeneity you have. The measures are, number 1, Gini impurity. Number 2, we have something called as entropy. Or number 3, we have something called as misclassification error. There are 3 kinds of measures which are popularly used, guys: Gini, entropy, and misclassification error. At least I would say 2. The third one, I don't see it anywhere, but at least the top 2, Gini and entropy. Well, let's discuss about all the 3. There are 3 measures available, which is pretty commonly used in many of your decision trees implementations you see in R and Python today. Those are Gini impurity, entropy, and then over to the last case, which is basically misclassification error. So these are the 3 different measures you will typically see. Using either of these 3 measures, right, you will go back and evaluate how much of heterogeneity. So say for an example, Gini will tell you, hey, the heterogeneity is 0.96, then it's a problem. Then probably the Gini impurity is saying in another case, hey, I got 0.05, then it is very good. Okay. So the Gini impurity, entropy, misclassification error, these are the probable metrics you will probably use to quantify how much of heterogeneity is available in a given node here. Okay. I'm going to come back to these measures in some time. So Hunt's algorithm said was, hey, go back and populate the entire data set to the root node, right? If the root node is evaluated using either of these measures, and if you see that the heterogeneity is almost close to 0, then let us call the root node itself as a leaf node. I don't think the data set needs more partition. Else we are saying go back and start the partitioning. I wanted to start the splitting process. This is where stage number 2 will basically start. What is stage number 2? So you have decided, okay, I populated my entire data set, it needs splitting right now, right? So what we're going to do is, guys, we are going to use certain variables. That is, we are going to use the best variables available with us, or let's say, I'm going to use the most important variable who literally gave us the best splitting criterion. So what are we doing? We are choosing the best splitting criterion here, using one of the best variables, that's all. The same an example as I told you, right? If there are 1,000 people standing right in front of me, I'll tell you what is the easiest and the best variable that you can use to split the 1,000 people. The first highly ranked variable would be something called gender, isn't it? Right? One of the easiest method and the best way to split that massive 1,000 population will be something like gender. Rather than doing an age group there, I have several other variables. I could have used gender, right? I could have used something like age of a person. I could have used the income of a person. I could have used the designation of these guys. I could have even done using the region that they're coming from, or the culture that they are probably having. There are a lot of ways of splitting the people. But who will be rank one? It will be gender, because immediately he reduces a lot of heterogeneity for me. Already it's like a lot of disturbed mixture, right? There's like male, female, lot of people together. I don't know how to kind of call it as a homogeneous mixture. No, it's not. So moment you split it with gender, that's it. Now you can call it as a homogeneous mixture. People on the left hand side are males and people on the right hand side are females. So he'll take best variable, rank number one. Then after I do it with gender, what else am I left off with? I'm left off with age, income, designation, the region they're coming from, the culture they have. I may probably be interested in the age group. So I can say, hey, okay, 20 to 40, 40 to 60, 60 to 80, 80 to 100. Let these be different age groups. So using age as a variable also, I can further divide the data set. So inside the male, I'll go back and tell, start creating 4 different groups. Inside the female group, I'll say start creating another 4 groups. Then probably I may start using the region they're coming from. Then I may start using the job designation that they're probably having. Then further inside, I may start using the income that they're earning. So what happens is, guys, you're basically going to start using the best variables at the very top, and you'll keep dividing them over and over on the insides, and you'll create small subsets. So what happens is, out of all the predictors available with us, x1, x2, x3 goes on till something like xn, we're going to choose the best variable to split upon. It's called as what? It's called as the best variable to split upon. How do we do it? Once again, using these measures, and it's more of a search here. It's more of a greedy search algorithm. Okay, I'll tell you how it happens. So it's called as a greedy search algorithm. Okay, we call it as a recursive partitioning algorithm. Okay, partitioning, whatever it is. Okay, it's a very greedy search algorithm, and it's basically using something called recursive partitioning method. So what happens is, guys, your entire data set is getting populated here on the root node. You are evaluating, okay, I was given 10 variables. Out of the 10 variables, what I will do is I'll go back and say, okay, all this n is equal to star. We will use something like age first. So here the impurity was 0.96. Here, what is the impurity? It is 0.90 only. Okay, so this is what age is doing. Then you will say, okay, how about region variable? If I use region, what will happen? Okay, here you had 0.96. If you use region, you will end up with 0.85. Seems good. Then you will try it out with somebody like income. Okay, so you had 0.96. At later stage, it probably became 0.80. Then probably you will try it with other variables like designation they are holding. Okay, the age of a person, whatever it is. You will try with gender also. When you try it with gender, the root node was 0.96, but the next set of nodes became 0.60. So it's a greedy search algorithm, guys. Why do I call it as greedy? Because he's worried about himself at that point. So he's saying, hey, this node has to be divided right now using one of the variables available here. I should try to reduce the heterogeneity as much as possible. I'm very greedy. Why? Because I cannot say like, it's okay, let me use income for now. At a later stage, gender might help us reduce it more. I'm not thinking, far afield, something like that. So what are you not doing? You're not saying that, okay, now let me make a bad step so that in near future, I'll come up with a much more better step. So what is he doing? He's a greedy search algorithm. He's saying, I'll make the best of it. Whatever is the best, I'm going to absorb it. I'm not going to reserve it for the next people that you see at the bottom. That's all. So it's a greedy search algorithm, guys. Why it's greedy? Because he's evaluating variables, like how many ever variables you have, right? He'll evaluate all the variables and he will check which variable, when I use this particular node, is giving me a maximum reduction. So when I use age, I get reduction of what? 0.06. When I use region, I get what? 0.11. When I use income, I get what? 0.16. But when I use gender, I get 0.36. So maximum reduction when I use gender. I will immediately start using gender only for me. So I will say, hey, this root node should now get split using gender as a variable. And I'm very greedy, okay? I'm not going to say that it's okay, let me use something like region and let me reserve gender, a very good variable, probably for the next level. I'm not going to do something like that. I am more worried about myself as of now. I'm not worried about what may happen in near future. I'm not worried about reducing what will happen in the coming levels. For now, my level, I should reduce the heterogeneity as much as possible. So that is the reason why we call it as a greedy search algorithm here. Let's please keep that in mind. Hunt's algorithm is a greedy search algorithm. It's greedy because unlike other statistical algorithms and all available, right, where they make a bad step so that in near future they'll come up with a good step, this guy is not going to do like that. He says, I am going to make use of the good step right now itself, and probably if there's any other good steps coming further, he may use it. Otherwise, I'm not really worried. It's a greedy search algorithm here. So what happened, guys? As I told you all, he's going to basically test. It's a search algorithm. He is using age, he used income, he used age, he used gender, he used designation, everything. And he found that gender is the person who gave him the maximum reduction in the heterogeneity. Probably here it was 0.96, but here it became 0.60. So the reduction was pretty massive. That is why out of all the 10 variables, he was going back, testing and searching the best variable to split upon here. That is why he has chosen gender for now. So he's saying, hey, male gender, you may have to come here, female gender, you'll have to go there. Then later on, what will happen? You will have other variables like age right now, income right now, region that they're coming up with, the designation that they hold. Now it will be a search. These 55 people here, they will check, okay, can we further divide ourselves using age? Or how about income? How about region? How much designation? Now they will choose, I think age is the best variable to split upon. This way will also ask, okay, I think we are left off with age, income, region, and designation. Which one do you think is best? Probably for these people, it could have been income as the best variable. So he will start using income. So for every level, they're going to search with whatever be the variables that is left off, right? They're going to keep searching. And we call it as a recursive partitioning method because it keeps happening in a recursive fashion. This node was there, I split it. It gave me 2 or 3 nodes. I split this guy, it gives me another node. I split this guy, it becomes again. I check these guys, I'll split it more. It keeps happening over and over and over and again till the last levels and all are having completely homogeneous subsets. That's why it's a recursive partitioning algorithm also. It's a localized search. It's doing a localized search. It's a greedy search. It's a recursive partitioning algorithm. It's having a top-down approach, right? From the top, it keeps dividing into small pieces here. It's having a top-down approach. It's creating an inverted V-shaped decision tree. These are different keywords you need to keep in your mind. Hunt's algorithm, a greedy search algorithm who's doing a localized search. It's a recursive partitioning algorithm because he keeps testing for homogeneity at each and every level. If it is already homogeneous, he's not going to split it anymore. But if it is not so homogeneous, he's going to choose the best variable to split upon, and he'll keep splitting them. It'll keep happening over and over and over again till you finally end up with small subsets which are completely homogeneous here. So this is exactly the role of your Hunt's algorithm, or it's more like the base for any decision tree model implementation you see in R and Python. You have something called as Hunt's algorithm. This serves as a base for all of your algorithms here. I mean, all of your decision tree implementations here. Okay. So root node, I'm populating entire data set, checking for heterogeneity. If heterogeneity is equal to 0, I'm happy. Root node is equal to leaf node. I don't even have to create a predictive model, which is rarely that's going to happen, 0% cases. Obviously, the heterogeneity is going to be above 0. Hence, we start doing the splitting process. For splitting, you need to even evaluate the heterogeneity and all, isn't it? For that, we have a couple of measures we're going to discuss. The names are Gini impurity, entropy, and misclassification error. Once I know that the splitting process is supposed to happen with all the variables available, I'm going to do a localized search. I'll do a trial and error. I'll check which of these variables are probably giving me the maximum reduction or a much more lesser heterogeneity compared to the previous level. Out of all the variables available, you choose a variable who's giving you the maximum reduction and you start splitting. Greedy search because he's worried about himself, not really preserving the best for the next levels. He's using it for himself. It's a recursive partitioning algorithm because it happens again and again and again till you end up with a very small data set. It's like a very recursive partitioning method. It's a localized search, as you all may know. You're doing it in a top-down approach to end up with the inverted V-shaped decision tree that looks something like what we've just drawn here. This is Hunt's algorithm, which is going to serve as the base for any decision tree implementation that we've seen in R and Python. I repeat it. Right? So you can see Hunt's algorithm, a base for any implementation of decision trees in R and Python. Okay. Yes, till here, are you all convinced, guys? So what is a decision tree? How does it work? And what are the parts of a decision tree? How does the induction of a decision tree work? The algorithm here, everything. We're going to see some cases and all. Okay, I'm going to help you all understand with a small data set here. We're going to do that. Till here, are you all convinced on how it's working? Yeah, it's not very statistical. It's not having any equations or mathematics, nothing. It's just plain logic. I just need some very good computer and very good coding experience. I'll keep writing for loops over and over and again, and I'll keep doing the same thing here. That's it. It's more of a machine learning thing. It's nothing to do with statistics and mathematics. There's just one place you will see an equation, this area. That's all. Otherwise, there is no formulas, nothing, whatever in a decision tree. It's more of plain logic. That's it. Okay. Okay. So I think Manohar has a question. Should the heterogeneity always be 0 to be considered enough to stop it? The splitting criterion? Actually, no. I'll talk about the splitting process. The stopping criterion here in some time. Actually, it's like they keep a threshold. Okay. It's like 5% of the heterogeneity available in the root node. 5%, 10%. Sometimes people will say 5 data points can be left off in the root node till that, in the leaf node, till that you need to keep splitting it. Here the 0 is more like a, more like a, what I would say, assumed number I gave you, but typically it's like a threshold. Like, you can keep 0.1, 0.2, those are the numbers. Anything below 0.1, he'll not even split it. If it's above 0.1, he will go back and split it. So this is a number that you can fix. You can fix the splitting criterion. Okay, so the stopping criterion or the splitting criterion, both are almost kind of same in this area. I'll tell you in some time how it works. But that's a nice question. So why do I call this as ML? Machine learning. Very simple. So you're not doing any work here. It's just certain algorithm. So you don't have to go back and find the patterns. The algorithm is going to do it for you, right? So you're just writing a simple one-line function. The algorithm will help you map what is the relationship between the predictors and the target, right? And it's a pure machine learning model. Why? Because there are no parameters and all that you're estimating. It's a non-parametric model. While linear regression, logistic regression, I call it more of a statistical model because there are parameters you're estimating. So what can happen is, from the parameters, you can go back and associate with your business. Last class, what did we do? We said, hey, for every $1 of investment you made, your sale is going to increase by $0.09, right? So you're able to connect it with your business. But you're in a decision tree, you can't connect it with your business at all. I think to a certain extent you can still do. The rules are there, but I'm just saying, you don't get any parameters or anything which can help you go back and connect to the business. So any predictive models where you're not able to explain why it's happening, or you're not able to connect it back to the business, right? Immediately you can call them as machine learning models. Okay, much more complex term will be black box, but there's another reason why we call it as black box. So I'm just saying, machine learning models is something that you may not be able to explain why it's happening. Directly, I'm saying, still you can do it. Okay, there are certain methodologies by which you can still do it. But directly from the model output, there is nothing that you can explain. But in statistical models, you can explain. Look at correlation, look at covariance, look at plain variance, mean, median, or look at ANOVA, look at chi-square, or look at linear regression, logistic regression. You get coefficients as an output. Using all of these coefficients, you can relate something to the business. You can make business rules. But here in machine learning models, you can't do it. They can just plainly give you predictions perfectly. That's it. Okay. So this is where I try to draw a line between statistical models and machine learning models. Once again, there are different schools of thoughts. There are different peoples with different ideologies. In my case, I would say even difference between machine learning and artificial intelligence would be just using deep learning models. That's all. Okay, machine learning means anything which is not involving deep neural networks or your artificial neural networks. So anything that's using artificial neural networks will be called as AI, artificial intelligence. But some people say AI is more of a very broad bubble and machine learning is more like a small piece into it. I would completely differ. It's called artificial neural networks. From there is where the name came, something called artificial intelligence. Okay, nobody agrees with that. But they say artificial intelligence is more like a very broad bubble. There, inside that is the statistics, machine learning, everything, fitting into it. It's more of a marketing jargon is what I would say. So ANN, artificial neural networks, gave birth to a new set of predictive models, a new era, right? Era itself, something called as artificial intelligence. Because machine learning was available even 5 years back. But artificial intelligence was available only in paper. We didn't have enough computational power to do it. But today, with the invent of GPU systems, etc., even AI is very simple to do. You have very good hardwares today. Machine learning is something that doesn't consume much of a hardware compared to AI, but still higher than statistical models. So it's all, in different, ages, different kinds of models were used. So you started giving it names. That's it. Okay. So why do I call it as machine learning? Because there are no coefficients getting estimated. An answer is so simple like that. Okay. So any questions still here, guys? Shall we just quickly take a small break? Nizam, what are the real-time applications of a decision tree? Sure. I'll just come back after the break and I'll tell you where are the different areas where you can see decision tree implementations. Okay. Great. Okay. So let's go for a 15-minute break, shall we? So let's be back at 6:55 Indian time. Okay. Okay. So thank you, guys. Let's be back in 15 minutes.
This conference will now be recorded.
Okay. Great. Okay. So let's get started. Okay. So I guess we have spoken about the decision tree induction, right? So how does a decision tree basically get created? So the base is basically something called the Hunt's algorithm, right? And we have spoken about the steps involved there. So what I'm going to do next is I'm going to jump into the impurity matrix that is typically used whenever it comes to evaluating a particular node for its heterogeneity. Okay. There are three commonly or popularly used measures, guys. I would say two. Okay, the third one is not very common. So the three commonly used metrics are Gini and entropy, and over to something called as misclassification error. Okay. So what is a Gini impurity? Very simple, guys. The formula goes something like this. So we basically write it as 1 minus summation of probability of I given the target taken to the power of 2. Okay, it is 1 minus summation of P of I given T taken to the power of 2. So this will give you something called as Gini impurity. So in entropy, it is nothing but minus of summation I runs from 1 till n pi times log to the base 2 of pi. So entropy is what? Minus summation pi times log to the base 2 of pi. And over to misclassification error, it is given as 1 minus max of, let's say something like P of I or P of J. Okay, so the Gini impurity is given by 1 minus summation of P of I given T taken to the power of 2. Okay, and here in entropy, it is given as minus of summation of I runs from 1 till n, where Pi into log to the base 2 of Pi is what you're doing. In misclassification error, it is basically given as 1 minus max of Pi comma Pj. Okay. I'm pretty sure all of you might be wondering, what do you mean by P? Why do you write a formula something like this? Let's jump into this Excel. Let's see here. So it's actually pretty simple, guys. So what we're doing is we have the frequencies, isn't it? So here, what did we have? We had the frequencies while we were talking about, the distribution. Instead of having frequencies, we are going to convert them as what? Probabilities, or more like proportions. That's all. So say for an example, there is one node, okay? It is having 9 people who are responding and 1 person who is non-responding, versus another node with 90 people who are responding and 10 people who are non-responding. So how do you convert it as proportions or probabilities? You say 9 divided by 10 and 1 divided by 10, which is 0.9 and 0.1. Here it becomes 90 by 100 and 10 by 100. It becomes 0.9 and 0.1. Or similarly, when you have 900 and plain 100, it becomes 900 by 1000 and 100 by 1000. So whatever it is, you're going to end up with percentages. So the distribution of each of these classes in every node, you're coming up with something called as percentages, probabilities, proportions. You can call them as anything, right? You're basically coming up with something called as probabilities. So going back here, guys, what you can see is I've cooked up different scenarios, okay? So there is one scenario where you've had a probability of one class to be 0.001, another class to be 0.99. Another case I've cooked up, which is 0.1 and 0.9. Another case is 0.2, 0.8. Another case is 0.3, 0.7. 0.4, 0.6. It becomes just the opposite. The direction keeps changing. So what we have is, we have all the proportions here and the opposite proportions here. Okay, basically probability of A happening, probability of A not happening, or otherwise probability of B happening, right? So now if you go back and see, guys, so what are the different formulas we have? We have plain probabilities. One guy is asking for squared probability. Another guy is going to do a max of 2 probabilities and all. So I think you need square, right? So let's go back. We'll make this case to be squared. We'll apply it everywhere. And here also we'll say, hey, this probability taken to the power of 2, and we'll apply it everywhere. So we have got individual probability squares. Now what is the next step? You need to go back and find the Gini. What is Gini? 1 minus summation of P of I given T taken to the power of 2. So what do you mean by this 1 minus summation of P of I given T taken to the power of 2? Why did such a formula come? Very simple, guys. So Gini impurity, right? Its definition is very simple. It's very, very simple. So the Gini impurity is saying, hey, so let's assume there are two buckets with us, okay? So one of the bucket is basically people who would respond. Another bucket is people who will not respond. Let us assume you have an unknown data point, okay? So actually speaking, the true value was that he responded. So the true value, you know, or the final outcome was that he responded to the campaign. But what are you doing? You are classifying that he is not a respondee. So what a Gini impurity is saying is, he's saying, hey, Gini impurity is nothing but the cost or the penalty or the error that you're going to probably face for misclassifying a particular point. He's saying what? A point who should have ideally been in this particular bucket, if he's going to some other bucket, right? That is the amount of impurity, and that is what we call it as Gini impurity, is he saying. So what are you saying here? So respondee and non-respondee, or let's say, I'll take it as true value and predicted outcome, okay? So if for one customer, I'm predicting that, hey, he will respond, okay? And the true value also is that he responded. So this is a good thing to have happened. Number two is I'm saying, I'm predicting that he is not responding, and luckily he has not responded also. But the third and fourth cases are opposite. I predict he will respond, but he's not responding. I'll predict he'll not respond, but he eventually responded. So these are the two cases that we don't want, the bad cases. So see here, guys, P of 1 into P of 1 plus P of 0 into P of 0 plus P of 1 into P of 0 plus P of 0 into P of 1. So the summation of all the probabilities should be equal to 1. We know it. Because 1, 1, 0, 0, 0, 1, 1, 0, these are the different cases possible. So the probability should ideally become 1 only, correct? What are these two cases? These are the impure cases, the cases that we don't want, or the error you will make. Basically, which guys? These are the two guys, isn't it? So what are you left off with? You're left off with P1 square, and you're left off with P0 square plus Gini impurity is equal to 1. Then I will go back and write Gini impurity is equal to 1 minus P of 0 square and P of 1 square, which is exactly what we wrote it as 1 minus summation I runs from 1 till n, P of I given the target taken to the power of 2. That's all. Isn't it, guys? So the same thing. Gini impurity told us that, hey, when he should have been in the bucket 0, you put him in bucket 1, or when he should have been in 1, you put him in 0. That is the error, or that is a Gini impurity. So we are computing in terms of probability. We are saying P1 into P1 plus P0 into P0 plus P1 into P0 plus P0 into P1. The last two terms are the impurities. The other terms, these guys will become squared. These guys will become squared. You have a 1 here. So 1 minus this one will give you the Gini formula, isn't it? Go back and check. That's exactly what we've written. So he is saying the way you need to find the Gini is find 1 minus summation of probability of 0 square plus probability of 1 square. He's saying what? Probability of 0 square and probability of 1 square, they need to be summed up. Then you need to subtract it by 1. The moment you hit enter, you will get the Gini value right now. The Gini value for this particular node is 0.0002. How about for the second guy? 1 minus summation of pi taken to the power of 2. Similarly, for the third guy, you can do it. For the fourth guy, fifth, sixth, seventh, I'll do it for all the cases. You can see that Gini impurity will basically follow a curve something like this, right? So what is he saying? He's saying this is the area where impurity will be at its highest because you have 0.5 and 0.5. Whereas here the impurity will be low, here the impurity will be low because you had 0, 100 percentage and 100, 0 percentage. So these two cases are pure case, while this is the impure case. It's highly heterogeneous case. While this is a homogeneous case, this is also a homogeneous case. While this is an impure case, that's why you can see it's a maximum. So here you can see the other middle cases and all. It's slowly reducing. Here it's slowly increasing. So this is basically how your Gini curve is going to work. Okay. So actually speaking, the distribution would have been like this. Okay. So the distribution would have been like this. So it would have been everybody and 0. Then it could have become a little bit of people here. Then it would have grown a little bit more higher. Then it could have probably grown a little bit more higher. Then it will become perfectly equal. Then it will be the opposite, this guy. Then this guy will reduce, he'll go high. He will reduce a lot, he will go high. Then it will become completely zero. So this is how you get a Gini curve that looks something. Okay. So here B increases slowly, they become equal. There A decreases slowly, they become 0 once again. So this is how the Gini impurity curve will behave. How about for entropy? We'll go back and say it is nothing but minus of this probability times log to the base 2 of this probability minus of the other probability times log to the base 2 of the same guy itself. That's all. So we are basically saying pi times log to the base 2 of pi with a summation at the front and a minus at the front, right? So first probability pi into log 2 of pi, make it as minus. Second guy also make it as pi into log to the base 2 of pi, make it as minus. Then add them together. So when you hit enter, you'll get this much of entropy. Let's apply it everywhere. Now you can see this is exactly how your entropy curve has come out. So your entropy maximum value is 1, while a Gini's maximum value is 0.5. Right? How about for a misclassification error? It's pretty simple. He is saying just find 1 minus max of pi comma pt. That's all. From either one of those people, just find what is the max and just do 1 minus max. So this will become your misclassification errors curve. I hope I wrote the correct formula. What did I write? Yeah, 1 minus max only. Okay. So it is what? 1 minus max of both of these probabilities. Out of P of A and P of B, whoever is max, right? Use that number and subtract it from 1. That will give you what is called as misclassification error curve. So the orange one is basically Gini, the blue one is your entropy, the gray one is basically your misclassification error curve. So this is exactly how the 3 different measures will basically work for the different probabilities that we have here. So here it became 0.5, 50-50, that's why maximum. Here it became 0, hence lesser. Here it became 100, hence lesser. And the 50-50 cases are the bad cases. We are not able to make any decision. So this is exactly the way by which the 3 curves, Gini, entropy, and misclassification errors are going to look like. Right? Following guys, still here? Did you all follow the 3 things? Gini, entropy, misclassification error? So the entropy is something that you guys might have seen it. In fact, if you go back to logistic regression, right, you would have seen the same kind of formula, yi times log to the base 2 of pi. You would have seen it in entropy. Same thing, same concept. yi times log to the base 2 of pi is what you would have had. Here it becomes pi times log to the base 2 of pi. That's it. Okay. So this is exactly how the 3 impurity curves are basically going to work here. Okay, so the maximum when the probabilities are equal, and it is very less when the probabilities are probably skewed. So this is how the measures are going to behave like. Okay. Now for better understanding, guys, let's go back and solve a quick problem. Okay, the decision tree induction. Let's see how it's going to probably solve here. So let us assume this is a data set that was given for us. Okay. We have variable 1, which you can see it's categorical type. We have variable 2, which is numerical type. Variable 3 is your target, which is categorical, which means it's a classification problem that we're going to solve right now. And by the by, the measures I showed you guys, it's a classification measure. Okay, let's please understand that. The 3 measures are classification measures. They are not regression measures. We are talking about classification now. Regression is just like, it's going to take us 10 minutes. There's just one small change, it will become a regression model. So target, categorical, hence its classification. We have one predictor variable who's categorical in type, one predictor variable who's more numerical or continuous in type. I hope everybody agrees with you. The next thing I want you all to understand before we jump into the problem is, how are the predictor variables being handled in a decision tree is something that we need to understand. Okay. By the way, I remember one question, the applications of decision tree. Okay. So I'll give you an answer in some time. Okay. Hope I don't skip it. Yes. So before we jump into the small problem, guys, we understand that there are two kinds of predictor variables. We have a continuous predictor variable. We have a categorical predictor variable. The question is, how are these variables going to be handled while doing the decision process? That is something that we need to understand before we jump into it further. So, guys, decision trees, right? Where they're going to do a split here. The splits can basically be of two types. One is, it can be a binary split. Number two is, it can be a multi-way split. That is, the decision trees, if they give you just two daughter nodes, it's called as a binary split. Whereas if it's going to give you more than two daughter nodes, it will become a multi-way split. Okay. So binary split, multi-way split is possible both for categorical and numerical variables. So first understand that any variable can take up two kinds of splits, binary and multi-way. But in different implementations of decision trees, different methodologies are followed. Example, if I'm not wrong, in C 5.0, no, it is only binary split. You cannot see anything more than that. But in CART and all, you can see even multi-way. In Shade, if I'm not wrong, he is also both binary and multi-way, if I'm not wrong. I'm not very sure, I'm just giving you a hunch, okay? So in CART, C 5.0 and all, it's actually only binary. He does only a binary split. But in other cases, there is multi-way also, which is possible. So the different reasons why they're doing it, I'll tell you why. But for now, just understand that there is a binary split possible, there is a multi-way split possible. And there are two kinds of predictor variables that we typically deal with, as all may know. One is continuous, another one is categorical, correct? So let's understand a continuous variable, something like age, okay? So what will happen is, guys, if it's going to be a binary split, it's pretty simple. He will just create two daughter nodes by saying, hey, age value less than X, age value greater than or equal to X, that's all. He will just do something like this. He'll just say age value less than X and age value greater than X. This will give you binary. He'll find us one single threshold and he will split it saying less than greater than. While for a multi-way split, it'll do a binning operation. So he'll basically say, hey, these are age values between 0 to 10. These are age values between 11 to 20. These are age values between 21 to 30. And here he will say, hey, anybody above 30. So here he will sort of do a multi-way split. He'll start doing a binning. So this is what? This is a binary split, while this is a multi-way split. In the same fashion, for a categorical also, what would happen is, if it is a binary split, right, let us assume we have something like gender. He will basically say, hey, let me split it like this. I will have somebody like male over here and something like female and others over here. One possibility. Then when I use gender variable, I could have even done a grouping like this. I could have had females here and male and others there. Or another possibility is I could have had others here and male and female here. So when it's a categorical variable, if it's binary split, guys, once again, the exhaustive search will search all these probabilities, possibilities. You know, he has to search for age. You know, he has to search for income. He has to search and understand how is designation working, how is region working, how is gender working. But within those cases, there are many possibilities. Age could have been binary like this, or age he can use multi-way. Which is best? He will choose it. So something like gender, is binary better? In binary, I have three choices. Is multi-way better? Where in multi-way it would have been something like this: male, female, and others, right? So within each and every variable, guys, there's another level of search he has to do. So how can I use the variable is another search he will do. Can I use them in a binary or a multi-way fashion? Okay, if it is a binary fashion, how should I use them? If it is a multi-way fashion, how should I use them? That's another level of deep search once again they will do. Luckily, you don't have to worry. It's all already done. It's all readily available. Just call the function, hit control enter, it will start running. Right? So this is exactly how it's going to work, guys. Every predictor variable can be categorical, numerical. They can be used in two fashions, binary and multi-way. If it's binary, in numerical, it's going to binarize it like keeping a single threshold. Ends. If it's multi-way, it's going to do a binning. If it's categorical, they're going to get grouped. Different groupings are possible. If I'm not wrong, it is 2 to the power of n minus 1 possibilities, which is, here you have three categories, isn't it? Gender, male, female, others. So 2 to the power of 3 minus 1 minus 1, which is 2 to the power of 2, 4 minus 1 is equal to 3. So first check, second, third. The number of possible binary trees for a categorical variable can be found like this: 2 to the power of n minus 1, and then you do a whole of minus 1. Okay. So this is how it's typically handled, guys. Categorical variables, which are binary and multi-way. So as I told you, it's once again another deep dive and an exhaustive search that happens on the inside. Okay, it goes on the inside and it starts doing these kinds of searches here. So quickly, what we will do is we'll jump into this problem. We understand that it's a classification problem and that you've been given a categorical and a numerical variable, right? So this is categorical and this guy is numerical. So we'll discuss on how to handle them. So what should you do? You should first go back and check how much of heterogeneity is available by populating the entire data set. So we're basically saying that, I need to create my root node. So we are going back and we're going to create our root node right now. Okay. So we're going to create a root node. N is equal to everything. Okay. So how many N do you have? You have basically 10 data points. Okay. So what do you need to check? You need to check the frequencies. How many people in either one of these classes? So you can see here, this is the root node, or also called as a parent node. A and B, there are 5 and 5 people. These are frequencies. But we are allergic to frequencies. We want probabilities. So we will say 5 divided by the total 10 becomes probability 50. 5 divided by 10, which is total 10, gives you another probability, which is another 50. So these are the two probabilities you've got, 50% and 50%. What is next? You need to understand the entropy at this particular root node, right? Only if it is like too high, you need to start splitting them. So you need to check what is the entropy at this node. How do you do it? Let's go back and use the Gini, right? Gini is what? 1 minus summation of P of I given T taken to the power of 2, which means probabilities needs to be squared. So I will say, hey boss, this is my probability, square him. Hey boss, this guy is also my probability, just square him. So I've got the true probabilities where they've basically got squared. Now what are we going to do? We're going to find the Gini by saying 1 minus summation of these two people will give us an entropy value of, sorry, a Gini value of 0.5. It's what? It's a Gini value of 0.5 here. Right? So 0.5 is actually speaking a pretty massive number because 0.5 is the maximum Gini possible. So we have got 0.5 as a result. So what does it mean? It means that you need to obviously reduce them. You cannot use them directly. You cannot call that this particular node will be the final node for us. You obviously need to split it. But for splitting purpose, you have two variables. You can use a categorical variable, this guy, or you can use a numerical variable like this guy. If this is a categorical variable, I have only choices. I can do a binary split only, isn't it? I can do only a binary split. But in this numerical variable, I can do a binary as well as a multi-way. Both are possible. I can do a binary, I can do a multi-way. Both of it is obviously possible. And if I'm going to do a binary, the threshold, right, they can be anything. They could be 50, they could be 40, they can be 30, they can be 36. The binaries can be anything. There are several other possibilities on the inside. So I'll say, even if it is going to be binary, there are different thresholds you can take. That is another level of detail. In binary also, different binding values you can make. That's another level of detail. So what we will do as of now is we'll just fix it to binary, guys. I'm not going to deep dive inside these ones because you already know, right? Because it's more of a search. It's a trial and error kind of a search. So I'm not going to be doing it. I hope everybody should be able to understand what might happen on the inside. What we will do is we'll just fix that it's going to be a binary split. So here, this categorical variable, if it were binary split, you will have what? Hey, variable 1. For people who are having 0, they will come into this node, right? And for people who are having variable value is equal to 1, they will come to this node. So this becomes one single node, and this becomes another node. So what are you doing? From the parent node that you have, right? So this is the parent node or the root node. If I'm going to use variable 1, I will end up with 2 child nodes like this. Variable 1 value is equal to 0. Variable 1 value is equal to 1. Okay. So what do we need to do? Go back. Who are the people who are having 0 as values? These guys and these guys. How many people? They are 5, right? There are 5 people, or 3, 4, 6. Here there's another guy. There are 6 people. So there are 6 people available in this particular node, while previously you had 10. There's another 4 people who are going to fall here. These 10 people, how are they? The distribution, it was 5 and 5, 50% and 50%. Now for these n is equal to 6 and this n is equal to 4, what should you do? You should understand the distribution. How is the A and B? So that you can evaluate further. So from these 6 people, we are able to observe that 4 of these guys are A and 2 of these guys are B. So what are we doing? We are saying the distribution is 4, 2. So 4 people belonging to the A category, only 2 people belonging to the B category. So converting it as probability, it will become what? 4 by 6 and 2 by 6, which is 66% and 33%, right? So see here, 4, 2, 4 people belonging to A, 2 people belonging to B, convert them as probability, 4 by 6, and here it will become 2 by 6, right? Similarly, on the other node, if you guys notice, you had 4 people, isn't it? What happened to these 4 people? 1, 2, 3, and this guy is the 4th guy. So let's go back here. So this is another node that you created. So out of these 4 members, it is 1, 3. 1 person belonging to A, 3 people belonging to B. So I'll just go back and say that here it is 1, 3. Go back here and we will say it is 1, 3. You guys can see it is 1, 3. Convert them as probabilities, it will become 1 by 4 and it will become 3 by 4. But we know that probabilities are not to be used. We need probability square for Gini. So I will just go back here and I will change the formula saying, okay, these guys needs to be squared here. Or shall we do it in the next step? Just introduce a line here. Okay, so I'm just going to convert them as squares. Okay, so we are going to convert them as squares. So we will say, hey, this is equal to this guy taken to the power of 2, and similarly we are going to do it for everybody almost. Okay, yeah. So we are basically taking them to the power of 2. That's it. So we don't need the plain probability or the plain proportions as it is. We basically need to take them to the power of 2. That's it. So after finding the probabilities, you have taken them to the power of 2 right now. What is the next step? In this node, you need to find what is the impurity. 4, 2 became what? 66 and 33. Then you converted them as probability square. You need to understand what is the impurity here. So you're asking, hey, how much of Gini is available at this node? That is equal to nothing but 1 minus summation of P of I given T taken to the power of 2. Let's find the Gini. He's saying is equal to 0.44. So the amount of Gini available here in this node is 0.44. How much of Gini in this particular node? Let's go back and find it. 0.06 and 0.56. We need to do 1 minus summation of these two members. It give us a Gini value equal to 0.38. So going back here, it will tell us it is 0.38. So I know that, and the previous case, Gini was 0.5, but post splitting them, this node is having 0.44 and this node has become 0.38. But I need it at this whole level, right? I don't need it at node level. I want it at the whole, decision tree level itself. This level, how much is the Gini is what we need to have. So what can we do? Can we find plain average? So I can just go back and say, hey, I can find the average, boss. It is nothing but 0.44 plus 0.38 divided by I have two nodes. So the average becomes 0.41. This is a good methodology of doing it. I could have just averaged out the impurities in all the nodes available at that level. That will give me the Gini at that particular level completely. This is a good method. It's okay. But one problem is, guys, here, let us assume it is 60 here and it is only 4 here, okay? There are 60 data points which gave us an impurity of 0.44 versus only 4 data points which gave us a Gini of 0.38. Is it even good to average them as it is? The point is, I'm saying, hey, 60 data points themselves gave me only 0.44, while 4 data points of these guys are able to give me 0.38, which is a very bad thing to do. While 60 guys are giving me 0.44, right? Here, there are only 4 people, they are still giving me 0.38. So it's not wise to just average them directly. It's not correct, because here there are 60 people who gave you this answer, while here there are only 4 people who gave you this answer. You can't just average them directly. It's not the right thing to do. That is why we're going to do a weighted average, guys. Previously, what did you do? You gave equal weightage to both the people, 0.5 and 0.5. That's why it became what? Sum product of this guy with this guy. Basically, he was doing 0.44 into 5 plus 0.38 into 0.5, which gave you 0.41. It was equal weightage that you gave. Now I'm saying it's not equal weightage. I have 6 people here out of the total 10, while this guy is having only 4 people out of the total 10. So weightage will become 6 by 10 for this guy and 4 by 10 for this guy. Now see, the impurity has increased a bit. You're saying it is 0.42 right now. So you can't say, hey, I'll give you 50-50 for both the people. I'm not going to worry about how many data points are you probably carrying. That's the wrong thing to do. You need to give them a weightage based on the number of data points you have. At this level, you're basically handling 10 people. 6 of these are here and 4 of these are here. So I will basically split them up. I'll say 6 people out of 10, 4 people out of 10 will give me 60 and 40 here. Okay. Similarly, can you all help me solve this one? So you can see here, for the second variable I'm going to test, we are using a binary split, binarized value of 32, less than 32, greater than 32. Less than 32, there are 2 people. Greater than 32, there are 8 people. The distribution is 0, 2. The distribution is 5, 3. So now tell me, guys, how can I go back and find the entropy? So at this cell, what is the ratio? Can you all tell me? What is the calculation we need to do there? Basically, convert frequency as probability. What should we do? Exactly. So it's 0 by 2, which is 0. And here it will be 2 by 2, which is 1. How about for this case? Give me both the cells, up and below. Five by 8 and 3 by 8. 5 by 8 here and 3 by 8 here. It will give me probabilities. But we are not interested with probabilities. We basically need the square of those, correct? So hence we are going to go back and say, hey, this guy needs to be squared. The other guy also needs to be squared. The bottom guy also needs to be squared. So we have got the squares of them. Now Gini at this node we need to find. How to do it? 1 minus summation of 0 plus 1, which is 0. Why? Because you've got a very pure node here, isn't it? There are 0 people belonging to A, but there are 2 people belonging to B. It's a very pure node. That's why you got 0. Here it should be 1 minus summation of 0.39 and 0.14. You got a Gini value of 0.47. Now it will think, if I keep 0.5588, isn't it a wrong thing to do? Right? So here it is only 2 people who are doing it, while there are 8 people getting handled there. 2 people giving a Gini of 0 is not a great thing, but 8 people giving a Gini of 0.1, 0.2 something would have been a great thing. So doing a plain average like this is not the right thing to do. So what should be the weightages, guys? Can you all tell me? Yes. So the weightage should be 2 people you're having in this node. So you will be 2 by 10. 8 people you're having in this node, you'll become 8 by 10. These will be the weightages. Now do you see that the Gini has gone up by certain units? It has gone up to 0.38, right? Then what will you say? You will say, hey, in the previous node, we've got 0.5 as the impurity boss. If I'm going to use variable 1, right, the amount of gain I will get is 0.5 minus 0.42, which is equal to 0.08. But the amount of gain I will get using the second variable is 0.5 minus 0.38, which is equal to 0. This is the variable where I will get the maximum reduction as much as possible. So they're saying he's the person who's going to give you the maximum reduction here. So he's the most important variable for us. So compared to both the people, variable 1 as well as variable 2, variable 2 is the person who's giving us the maximum reduction when I'm comparing it with the node. So out of both the choices, I would ideally use variable 2 to split upon in this particular case here. So this is exactly how you choose the best variable to start splitting upon. So what are you going to do? So basically you're saying, hey, this was my original data set. I'll copy it and I'll paste it here. So we are saying this is my original data set. This original data set is right now getting divided into 2 portions using variable 2, right? The first portion will be less than 32. The second portion will be greater than 32. So let's go back and check who are the values less than 32. This guy and this guy. These are the 2 people. They will come under this particular node, while the other people will all go into the other nodes. So copy, paste it here. Okay. So what do we have? You can see. So that was a data set. You have basically divided them like this. So you're saying after dividing, we are ending up with 2 daughter nodes. This is the first daughter node you have, and this is the second daughter node you have. What is the Gini value here? The Gini value is 0, which means no more splitting is required. While here, what did you have? You had a Gini value of 0.47 something, isn't it? You have 0.47. So now we are saying here the Gini value is still a little high, 0.47. It needs more splitting. It needs what? It needs more splitting right now. Now what will you do? You'll say variable 1 as well as variable 2, both the people are available. Using this data set, I need to right now go back and check who is the best variable to split upon. Probably now variable 1 would have been a good variable. Hence we are saying, okay, variable 1 value equal to 0, these are the people here, while variable 1 value equal to 1, these are the people here. So further you are dividing the data set into something like this. So this data set further got divided into something like this. Then what do you see here? It has become almost homogeneous, but there is one B. Here also it is almost homogeneous, but there is one A. If it requires further division, you'll go back and divide them again. So this variable 1 has become 0, right? You can delete it in fact. It serves no purpose. Variable 1 has become 1, you can delete it. It serves no purpose. So obviously using variable 2 only, you need to split it further. Even here also using variable 2 only, you need to split it further. Okay. So this is exactly how it's a recursive process, guys. So this data set will be further divided. So I'll probably say, hey, these guys here. Sorry. So all of these guys here and this guy alone probably here. I can divide it further like this, right? Even here you will say, hey, this guy alone here and these two people over here. So you'll probably end up with 4 nodes, something like this, 4 leaf nodes, something like this. So this is one leaf node, this is another leaf node, and this is probably another leaf node, and over to the last guy, which is another leaf node. Okay. So ideally, I don't think we're going to split it any further because, typically what happens is if the impurity value is less than 0.1 or something and all, it will stop. Okay, so 0.1 or something is kept as the stopping criterion. Okay, if your Gini value is above 0.1 only, it'll go back and split it further. If it's less than 0.1, it'll not at all worry. It says it's okay. And similarly, only if the number of data points that you have are greater than 5, right, it will split. If it is less than 5, it will not split anymore. So only if both the conditions are getting satisfied, where the Gini value is above 0.1 and the number of data points you have is above 5, it will typically divide further. Else it will not divide, actually speaking. So let us probably assume that we are not dividing it further. Okay, I'll tell you what will happen if you're not dividing it further. So let us assume we are not dividing it further. This becomes leaf node 1 and this becomes leaf node 2. That's all. Your decision tree is ready. Now what will happen tomorrow? Tomorrow there'll be an unknown data point. So you're saying, hey, I have an unknown data point. He has variable 1 and variable 2 values. Okay, so these are the two values you have, variable 1 and variable 2. He is carrying a variable 1 value of 1, okay, and a variable 2 value of 35. So what happens? This is your first criterion, right? You said less than 32 and greater than 32. This is the first criterion you had. So you'll check what is his variable 2 value. It is what, 35. So what will happen? He will be passed on to this particular node. So you're saying, okay, right now you're available here. Okay, you're available with this guy. What is the next condition? You're asking variable 1 value. Are you 1 or 0? He says, hey boss, I am 1. So he ends up here. So this data point is basically very similar to the population available here because he has the conditions satisfied by these people available here. So now you are saying, okay, historically, people who have satisfied these conditions, right? The number of A people was 1, the number of B people were 2. So I had just 3 people who satisfied these conditions. The number of A were basically 1, the number of Bs were basically 2. Now you're saying any person who's going to satisfy this condition, right? The probability of them being equal to A is 0.33, which is 1 by 3. And the probability of them being B is equal to 2 by 3, which is 66% right now. So what will you say? This unknown data point who is satisfying all of these conditions is getting passed on to this particular leaf node. Historically, this is the numbers we saw. Hence, we are saying this particular unknown data point is having a 33% probability of belonging to class A and a 66% probability of belonging to class B. Or there is a 33% of him responding and a 66% probability of him not responding. That's all, guys. This is exactly how your decision tree model is going to get created. So very simple. He's just saying, using historical data set, I'll try to segment the data as much as possible. After segmenting, on the inside, it is just a very, very plain probability formula. That's all. There is nothing fancy here, guys. All decision tree is doing is, it is just segmenting the data set into small subsets. Then into that particular subset, it is applying plain probability. There is nothing fancy here. No equation, nothing. Then he is saying, anybody who's following all of this condition and is falling into a particular segment, they are also most likely to have the same probability. Hence, you go back and assign that probability to that unknown member who's satisfying the condition. That's all. Very, very simple predictive model decision tree here. He's just segmenting the data set to very homogeneous clusters. That's it. So anybody who's satisfying this condition, so historically I found the probability. Same thing like naive Bayes, isn't it? Naive Bayes also historically you computed all the probabilities and you kept it. Then for any new person, you just ask the question, okay, what characteristics do you have? Based on that, I'll predict whether you are a banana, orange, or a whatever be the other fruits. Similarly, here you're saying, so based on your values and based on my historical data, and I'll check what are the conditions you're satisfying. I'll assign probabilities for you. That's it. This is exactly how a decision tree predictive model is typically created, guys. And what we are seeing here is more of a classification decision tree. It's a decision tree classification. Okay, we're not doing a regression tree. It's a classification tree, what we have seen just now. Okay. So I think Sanjay has a question. So going back to the question which you had mentioned earlier. So how do we determine 30 to be used for a binary split for a continuous variable? Okay, I'll tell you. Okay. So before we move any further, guys, till here, are you all convinced on how a decision tree model is getting created? How is he creating smaller and smaller and smaller subsets here? Yes or no, guys? Yeah. Okay, perfect. So going back to the question, right? So how did I choose a value something like 32? Once again, it's an exhaustive search, okay? What happens is he's going to try for different thresholds. That's all. I've kept 32 because I would have probably found it is the best. So how did he find it? I'll tell you. Basically copy all the values and keep it somewhere here, okay? Then you basically have to sort them. Okay, it'll do a simple sort. It'll go back and find thresholds by doing average of every adjacent member here. So between 30 and 31, what is the average? You have got 30.5. So this is a particular threshold it will check right now. Okay. Similarly, between 33 and 42, I think there is like 7, 8, 9 units of difference, 4.5, which is 37.5. He's going to use 37.5 as a threshold next. The next threshold he will use it between these two people, 49.5. Okay. So in this fashion, he'll keep searching for different thresholds. So I've just come up with a threshold something like 32 randomly to solve the problem. But how he will do is he'll go back and find all the different possibilities. He could have used all these things, 30, 31, 33, 42, everything could have been a possibility. But he's not going to use everybody because the time is going to be pretty high. It'll be very complex. That is why he's going to take up every adjacent member and he will find the average of those people. And those people will be used as the thresholds. So between these two people, it is 54.5. Between these two people, 56, 21, 10.5, 10.5, which should have been 66.5, I assume, whatever it is. Okay. So you can see here. So these are the 5 thresholds he should have ideally used. He would have kept less than 30.5, greater than 30.5, less than 37.5, greater than, less than greater than 49.5. These are the 5 combinations, or sorry, 5 possibilities he would have searched when it comes to variable 2. He would have done the same thing again. The same computation, he would have done it again here for another threshold, for another threshold, for another threshold. He'll compare with all the cases. So comparing this one with this one, with this one, with this, with this, with this, then he will choose which variable or which combination gave me the best variable to split upon, or gave me the least reduction, sorry, the maximum reduction. So it's an exhaustive search here. He'll go back and search for every combinations here. Okay. Is it okay, Sanjay? Did you follow the point? How it's doing? It's same for others. Did you all follow? Is just finding every adjacent member's average, and every adjacent member's average will be used as a threshold here. That's it. As simple as that. Okay. So if everybody has followed it, I think I'll solve another problem probably with entropy. It's once again pretty quick. So you can see here, guys, this is a data set we have, a small data set I've cooked up. So we have a target variable which will tell us whether a customer is buying a product or not, computer or not. So let's use, a categorical variable like, let's say, high, medium, low was income. I'll just do it for one case, okay? Because the same thing like what you saw in Gini, the formula alone is changing, that's all. So target is by computer, yes or no, 9 and 5. You need to convert them as probability. It'll become 9 divided by 14, and here it'll become 5 divided by 14, right? Then how do you find entropy? Minus of pi times log to the base 2 of pi. Similarly, minus of pi times log to the base 2 of pi. So you've got an entropy which is pretty high, 0.94, right? Now what we're going to do is we're going to use income variable, high, medium, low. Let's do a multi-way split. So high, medium, low. There are 4 people with high values, 4 people with low values, 6 people with medium values. How are the 4 people getting distributed? 2, 2 fashion. 2 people belonging to yes, 2 people belonging to no. How about these 4 people? It's 3, 1, 3 people to yes and 1 people to no. And there are 6 people here where it is 4, 2, 4 yes and 2 no. So totally there are 9 people yes and 5 people who are no. So now tell me guys, we're going to go back and find the entropy at each and every node. So this is the first node, high, okay? So the distribution was 2, 2. So the values that you have are 2 and 2. I need to convert it as probability. It will be 2 by 4 and here it will be 2 by 4. Then I need to find log to the base 2 of these probability. Okay, the log to the base 2 is this much. Then we need to basically find the entropy, the total entropy, which is equal to minus of pi times log to the base 2 of pi. I'll just keep a bracket. So pi times log to the base 2 of pi. Then another minus of pi times log to the base 2 of pi. So it gives you an entropy which is equal to 1. Why? Because it is 50-50%. So here it is 3 and 1. 3 here and 1 here. So it will become what? 3 by 4 and here it will become 1 by 4. I'm just going to drag this log to the base 2 of pi here. Okay, so you've got the log to the base 2 of this one, and I'll just copy and paste this formula so you can see. Pi times log to the base 2 of pi, summation is what he is doing. You have this entropy. Similarly, here it is what? 4 and 2, which will become 4 by 6, and here it will become 2 by 6. And you've got the entropies here. That's all. So the entropy of the first node, entropy of the second node, entropy of the third node. What can I do? I can basically do a plain average, but that's not what we're interested. We need the weights. Can you all tell me the weights, guys? The 3 weights here. Can you all give me the 3 weights that I should be using? Perfect. So we have 4 people here out of the total 16 people, right? Similarly here 4 people out of, sorry, it was not 16, 14, right? Yeah, 14. So here also we have 4 out of the 14. Here it is 6 out of the 14. So find the sum of it, you can see it's 100%. Then you need to do weights into entropy. Okay, then you need to find what is the total entropy at that particular level. So the total entropy is 0.91. What is the gain? How much did you have at parent? You had 0.94. How much do you have now? 0.91. Find the difference between them. That will give you how much of gain you have. So the gain is basically equal to 0.02. So in this fashion, you need to go back and do it for all the variables that's available here. Do it for age, do it for income, do it for student or not, credit rating, how much is it? Then check which variable is best and start creating the decision tree model. Okay, so this is how you create a decision tree model, by checking for each and every variable here, guys. And we have done it for Gini and we've done it for entropy also. Misclassification error, I hope it's explanatory, right? The same thing but a different formula, that's all. Yes. Are you all able to follow till here, guys? Are you all convinced with the methodologies, etc. here? Yeah. Okay. Perfect. So I think with this we are done for the day. So these are the portions that we had to discuss for today. Okay. I think just one or two things are there. We just have to discuss how it works for regression. It's very simple. It's going to take probably 15-20 minutes max, something even less than that. And then probably for tomorrow, we can jump into other extension of these predictive models like bagging, boosting, random forest, etc. So since they are all the same class of predictive models, let's probably discuss those members. And then we can go back and compare the performances of each and every person also. So we'll have that kind of an exercise. Tomorrow we'll jump into bagging, boosting, random forest. I think time is going to be short. It's going to help us discuss only about bagging and random forest, I guess. Okay, so boosting may not be able to be completed tomorrow. So I think bagging and boosting should be good enough to be completed tomorrow. Okay, great. So is there any questions, guys? Can we call it a day? Are you all good till here? Conceptually, everybody is good? Oh, thanks, Yatendra. Awesome. Okay, great. So then let's call it a day. Yeah. Oh, thanks, Manjeet. Thank you. Okay. Okay. So thank you, guys. Thanks for joining. So let's catch up tomorrow where we discuss the rest of the predictive models. Okay. Thank you, guys. Thanks. Bye.